The next example we're going to look at is from thermodynamics. And here's the situation. We have a ring, we have an outside border and an inside border, and what our interest is what is the temperature at any point R within this ring if there's a certain temperature on the outside border and a certain temperature on the inside border. And so we have an initial condition on the outside border when our radius is B, U of B is U1, and on the inside border, U of A, when the radius is A, is U sub 0. And now I'll go back to the problem to show you what we're interested in. What we're interested in is the temperature at position R within the circular ring, and that can be determined by this boundary value problem here, R times second derivative of U plus the first derivative of U with respect to R is equal to 0, with our boundary conditions as given below for U1 and U2, or U1 and U0 constants. So what we're going to do is show that we can find that temperature, U of R, by using this formula, U0 times ln of R over B minus U1 times ln of R over A, all that divided by ln of A over B. So, to start to solve this equation, we would multiply both sides by R, and then we've got ourselves a Cauchy-Euler. So we assume a solution of form U equals R to the M. U prime would be M times R to the M minus 1, and U double prime M squared minus M times R to the M minus 2. So the characteristic equation is R squared times M squared minus M times R to the M minus 2 plus R times M R to the M minus 1 equals 0, and therefore if we factor out R to the M's, actually this should be R to the M here, we wind up with M squared minus M plus M is equal to 0. So that's M squared equals 0, so we got a double root of M equals 0, so we got solutions U equals C1 times R to the 0 plus C2 times R to the 0 times ln of R. That's what you do when you have a double root. If you want to go back and look at case 2, unit 3, lesson 6, you'll see that that's the case. So, boundary condition given this one, when R equals A, U is U sub 0. What does that mean? Well, when R equals A, this is ln of A, and this is U0. So U0 equals C1 plus C2 times ln of A. Similarly, for our other condition, right, U1 equals C1 plus C2 times ln of B, and we can now solve this system. U0 equals C1 plus C2 ln of A, and U1 equals C1 plus C2 ln of B, using Cramer's rule. We're trying to find C1 and C2, of course. So C1 would be, we put the coefficients of C in the denominator. That's 1 ln of A, 1 ln of B. That's from this one, this ln of A, this one, and this ln of B. And in the numerator, we put the same thing, the same determinant, except we replace the 1 here and here, here and here, with U0 and U1, the other side of the equation. So, therefore, our C1 is U0 ln of B minus U1 ln of A divided by ln of B minus ln of A. In a similar fashion for C2, straightforward. We already know the denominator. We replace the ln of A and ln of B with U0 and U1, and then we get U1 minus U0 times ln of B minus ln of A. So now the solution to the boundary value problem is U equals C1 plus C2 ln of R, but we got our C1, and it's this. And we got our C2, and it's this. So that's going to be multiplying the ln of R. And a minor adjustment here would be, I switched around, notice what I did, I switched around the signs of the numerator and denominator for both, because I know where I'm heading. I want to have ln of A over B in the denominator, so I can't have ln of B minus ln of A, I need to have ln of A minus ln of B, because ln of A minus ln of B is ln of A over B, and that's what I'm looking for, right? So, I did switch those around. And so now, if I added these two together, since I had the same denominator, I would get u1 ln of a minus u1 ln of r, this one kind of snuck over there, and u0 ln of r, that's this one, minus u0 ln of b, that's this one, all over ln of a minus ln of b. Well, you're probably wondering, what's that all about? And the answer is, well, look. Factor out my u sub 0, I got u sub 0 times ln of r minus ln of b, which is ln of r over b. Factor out my u1, I got ln of a minus ln of r, which is ln of a over r. So there's u1 as stated, or u0 ln of r over b minus u1 ln of r over a, which is pretty terrific that I got it to work out like that. Oh, it's not terrific that I did that. I want this to be subtract in there, and for some reason or other I'm having trouble getting it to say that. No, that's not quite it. Okay, I made some minor adjustments, and I think I have it right now. u0 times ln of r over b minus u1 times ln of r over a over ln of a over b. So I think that was what I wanted to show, and that means if we wanted to find a temperature at some radius from the center, like maybe here, or here, or here, we just need to know what r is, and we could run r through this. It would be u0, this number, times ln of r over b, minus u1, that's this number, times ln of r over a, all that divided by ln of a over b. I hope that's what we wanted to show. And lo and behold, that is what we wanted to show. I guess, well, probably could have said this as u of r. There, now that's better. And that's what we wanted to show, and that's the last video for Unit 3.
I sincerely hope so.
Bye.